I want to welcome everyone to the Fermentation Association's webinar, Better Wine Production with Inline Optical Monitoring. I'm Mo Langer, TFA's Marketing Director. We are a trade group that was launched to support producers who use fermentation to create delicious and often healthful foods and beverages. Our goals are to help educate consumers about fermentation and its benefits, support scientific research into those health benefits, and work with food safety authorities to establish clearer and more appropriate regulations in regards to fermentation. Occasionally, we also have the opportunity to present new and innovative products and services to our audience, as we are doing today with this Vendor Insight webinar brought to you by Tech5 USA. I am pleased and excited to introduce today's speaker, Dr. Amanda Muraca. She is Tech5 USA's Head of Business Development and Application Science for chemistry, petrochemistry, food, beverage, and agriculture industries, where she helps develop solutions for difficult analytical challenges. We have many questions already submitted and reviewed with our speaker. If there are any other topics you'd like to see addressed during the presentation, please enter them in the chat below, and we'll try to get to them after the formal presentation. So with that, I will turn it over to you, Dr. Muraca.
Thank you very much for that introduction, Mo. I am going to start by sharing my screen. And let's see if we can get this going. Okay, so thank you all for joining me today. Today, I will be discussing spectroscopy for the winemaking process. And I have shared with you today just a brief overview of what I will be discussing, primarily how spectroscopy can be utilized to assist in the winemaking process, and overall discussing QA/QC for wine production and some of the parameters, as well as traditional methods and the advantages that spectroscopy brings. And then I will discuss some of these application details, including ethanol fermentation, anthocyanin, and tannin, as well as additional potential parameters. And then I will discuss Tech5 USA specific hardware and then summarize, and at that time, take any questions that you may have. So looking at this kind of flow diagram of the wine production procedure, I know this is probably very familiar to many of you, but just generally from harvest to consumption, there are many steps that are relevant to the winemaking process. And throughout this process, there are key parameters to understanding your process fully and ultimately optimizing your process for highest quality product and highest efficiency. So looking from harvest to extraction to fermentation, pressurization, filtration, aging, bottling, and consumption, there are key parameters to measure. I've included here just some examples of these measurement parameters, probably some of which some of you are currently monitoring. And of course, this is not the limit to the key parameters that are critical, just to name a few. Looking on the feedstock side, there are key parameters on the harvesting portion, such as nitrogen, moisture, protein, and starch, which are critical. And looking on the processed material, some of these parameters include glucose, ethanol, acidity, anthocyanin, and tannin. And again, these are just some of the parameters that are key to understanding the process. Traditionally, these parameters have been performed and understood with traditional analytical methods that primarily take place in the laboratory. These include high pressure liquid chromatography, or HPLC, densiometry, gas chromatography, or GC, and all of which introduce some sort of lag time in the measurement. So you could see on the right-hand side here, ultimately, in the case of ethanol, you can obtain your percent volume concentration for your sample, but sometimes, these are delayed up to several days. So this requires pulling the sample from your process, packaging it, sending it to a laboratory that's, provides the relevant information, and waiting for that result. In the case of all three of these methods, the measurement is ultimately destructive to the sample. So I mentioned, bottling up your sample and bottling up your product and sending it off. And then ultimately, this product cannot be used, ultimately in the end. So all three of these are destructive. And then taking a closer look in the details, when it comes to high pressure liquid chromatography, this often requires expensive consumables such as organics materials or organic chemicals, which can, of course, add up, per measurement each time you require it. In the case of densitometry, this is a well-known method for ethanol detection, but it is limited in the number of analytes that it can be performed for. So again, this is ideal for ethanol, but ultimately, if there are additional parameters that are required, the end user will have to find the appropriate laboratory to perform those measurements. So again, limited in the sense that it is a good technique for ethanol, but is somewhat limited there. And then in the case of gas chromatography, there is ongoing cost for each measurement. So there are carrier gas that are associated with it. And each time you have to perform a measurement for a particular sample, it's a different sample run and a different cost associated with each measurement. So although these traditional laboratory methods do provide accurate results, there are some disadvantages to them. Looking at the advantages of Tech5 USA and spectroscopy solutions, I've listed a few here. Ultimately, this technique is non-destructive. So it utilizes optical spectroscopy, which is the technique of just how light interacts with matter and does not destroy or degrade the sample. So ultimately, the measurement you perform, that product can then be used in a final product batch. It also quantifies several components simultaneously. So if you're looking in a wide spectral range, in the near IR range, for instance, you have a few different key regions that are associated with various components, and just pinpointing those different regions can allow you to quantify multiple components with a single measurement. It also allows for real-time data acquisition. So these measurements can be performed on the order of milliseconds to seconds. So the data that you're getting in real time is significant to what you're actually looking at in your process. So because of this seconds to minute measurement, you can make real-time decisions based on the results. Ultimately, this is a maintenance-free sample preparation. So you can see on this image here, I've included two of our example instruments here. And you can locate these instruments via fiber optic probes and fiber optic cables at different locations on the process. So if you want to monitor the incoming feedstock, you can essentially stick this probe into this particular inlet and have real-time data acquisition. You can alternatively look at measurements directly in situ within the fermentation tank, or some bypass loop where some material is pulled from the sample and redirected back into the tank. And then finally, if you want to look at outgoing product for quality, you can also immerse this on an outlet port. And a great advantage to this is that you are not sacrificing too much sensitivity and accuracy when it comes to the measurement. So although, laboratory measurements are performing with high sensitivity and accuracy, you can achieve similar sensitivity and accuracy with near IR spectroscopy in real time. And then finally, the one final advantage is the ability to have closed loop control. So ultimately, the decisions that are made from the results can be set up to be automated if the end user chooses to do so. So either manual decisions and manual actions being made off of these results, or automated control is also a possibility. So I mentioned earlier the different steps and the different procedures for wine production. And since this is a fermentation presentation, I thought I would focus a little bit more on the fermentation portion of this. So there are key parameters to monitor in the fermentation process, and I've just chosen a few to discuss in more detail here. So this process of alcoholic fermentation is I'm sure, very familiar to many of you that are participating today. The process of converting sugars to ethanol ultimately. And that's done, of course, in the presence of yeast and forming carbon dioxide as a byproduct here. So in the case of the fermentable sugars, two examples of those include glucose and fructose, which are some of the main components. And ultimately, 1 degree Brix or 1% sugar transforms ideally to about 0.55% ethanol. So the goal here for many end users and many operators is to ultimately optimize this efficiency, the fermentation efficiency, until the desired ethanol concentration level is achieved. So this is all too critical for operators to know the ethanol concentration in real time, as well as the declining sugar levels or fermentable sugar levels in their process. So taking a closer look here of the ethanol fermentation process for white wine, I have here on the right-hand side spectral results for white wine fermentation process. So you can see on the lower portion of the legend is from 0 to 100%. And this just indicates the percent completion of fermentation. So 0 being the baseline or the start of the measurement. And then as you increase to 100%, this is the point where the targeted ethanol levels were achieved. And looking at the spectra itself, we're observing the absorbance spectra of the white wine sample in the near IR spectral range. So looking at this inset here in red, this is the absorption between 1650 and 1775 nanometers. And this is due to the first overtone region of the CH groups in ethanol. And looking at this region here, you can take a quick snapshot and look at a first derivative of this absorbance spectra. So what this first derivative does is it allows you to look at the trends in the data and, ultimately correct for any baseline levels. So focusing in on this region here, if you look at this particular peak, you can see at around 0% or so, the intensity is fairly low in this region for ethanol. And as you go to longer process of the fermentation and you increase the fermentation process, you get increasing levels of ethanol. Ultimately, topping off here at around 100% or so, which is associated with the highest ethanol concentration. So this range here can be directly associated with the concentration level from, as we talked about, from 7 to around 18% or so. And ultimately, this output value can be, chosen and reported to any sort of measurement location. So very similarly, since we're looking at ethanol, it's a very similar result in the case of red wine analysis. So looking again here at the same absorbance spectra, first derivative of the absorbance, you can see here the increasing intensity of the absorbance peak as you increase the process of the fermentation. And as I mentioned in the last, this is directly associated with the increasing ethanol levels as the process undergoes. So taking one example of the fermentation process there, another example we'll talk about in the next slide. This can be utilized within the fermentation procedure, or sometimes this is an important parameter in the aging process for users to monitor. So this parameter is the anthocyanin and tannin ratio, or individually concentrations of anthocyanin and tannins. As many of you already know, the phenolic groups influence taste, color, and mouthfeel. And these phenolics are released from the solid parts of the berries into the must. In the case of the tannins, it is in the location of the seeds, the stems, and the skins. And the anthocyanins are primarily located in the skins. So this time period that they're located in the must is a critical parameter to influence the anthocyanin to tannin ratio. So getting this optimal ratio between the two, which is on the order of 1 to 4 or so, can be done with spectroscopy. So in the red wine making business, this fermentation process typically takes place in the presence of the skin and seeds. But in the white wine making process, the skin contact period is significantly minimized because, with white wine in this case, the anthocyanins, of course, influence the color. So white wine should not have too much of that contact period. So ultimately, the goal for the operators is to calculate that A to T ratio in order to determine the optimal timing for removal of the solid particles from the must. So here is another example of the spectral results for a fermentation process. In this case here, you can see from 0 to 100% or so. And in this particular measurement, the anthocyanins, or the berries, and were not removed from the procedure at all. They were left to stay throughout the entire process. So you can see this particular measurement ranges from 300 nanometers to 700 nanometers. So this is a UV vis measurement of this red wine. So breaking it down into two different components, you can see the absorbance in this region here has an absorbance peak intensity between 350 and 360 nanometers. And that absorption is due to the phenolic compounds. In this case, that is the tannins. So as I mentioned, they're found in the skin, seeds, and stems, and they are responsible for mouthfeel and taste. And then looking at this increasing intensity from 0% here, which is a lowest amount of time that the skins have been in the must. And then as you increase the length of time that these are within the broth or in the must, you see the increasing intensity of the tannins in this case. Looking into the visible range, around 520 nanometers or so, you see the absorption due to the anthocyanin. And these anthocyanins that are present ultimately lead to the increase in color intensity, which is why we're seeing, a significant absorbance in the visible region in this case. So it's very similar to the last at 350. You could see the increased intensity in concentration, or in the absorbance, as you go to longer lengths of time. And this directly relates to the prediction of the total anthocyanin. So allowing you to get a concentration measurement of the levels of anthocyanin, and ultimately you're able to determine this ideal A to T ratio in your broth. So looking forward, those are just two of the key parameters that I've talked about. There are additional parameters, of course, that are able to be monitored with this technology, but I just wanted to talk in some detail about the technology that's offered. So Tech 5 USA has, as I mentioned, UV visible and near IR spectroscopy solutions. But just talking about some of our products that have been used for these measurements include the compact near infrared spectrometer, and we so lovingly refer to it as the seniors, CNIRS. And this device has a lot of key advantages to it. It is compact in size and very robust in nature. And the compact size is in large part due to the inner workings. So you can see on the bottom here some of the inner workings of the device, looking at the spectral sensor here below. And this is an example of the device structure where you see this sort of stacked layer of PCB boards and detection apertures and so on. And then finally, the embedded electronic boards. And I'll go into some detail in a slide or two about the boards, but just here focusing on the compact nature. You can see a pencil here for scale that really contributes to this device having a very small footprint. So in addition to these components, these are equipped with MEMS or microelectromechanical system devices, and in this case here, a Fabry-Perot interferometer. So not only do these pieces of equipment allow for the compact size, but they also introduce a lower cost sensor as compared to conventional spectrometers. So this particular device utilizes the same in-gas detector type, but a tunable wavelength range in the range of 1.1 micron to 2.5 micron. So that tunability allows you to tune in on the relevant wavelength region, which ultimately contributes to the lower cost. So you're focusing in on the relevant wavelength region instead of getting the full wavelength range for the measurement. And these devices here, as you can see, are very suitable for a harsh industrial environment. So looking on the left-hand side, you can see the Class 1 Division 1 classified system for hazardous locations. And this device is explosion proof and has been put into or can be put into more robust and explosion proof environments. And looking at this device on the right hand side, this is an IP65 enclosure with protection against water and dust, and ultimately can be integrated into that harsh industrial environment as well. So just looking in some detail of the near IR spectrometer solution, you can see some of the specifications here include a Haslock C1D1 group system with the same module, single element module within the device. And ultimately, the resolution is on the order of 15 to 21 nanometers with signal to noise of 10,000 counts or so. It is also equipped with a 2 times integrated halogen light source and allows you to monitor the lifetime of your lamp via software. And then ultimately, the output results and status messages can be programmed to connect with a process interface via Modbus TCP IP. I mentioned previously the miniature halogen lamp. This has a very compact design, as all the other portions of the device do. And it's also built, as you can see, with these two dual halogen light sources here. So the functionality of these dual light sources is to automatically switch from one light source to the next if there's any kind of intensity drop. So this intensity drop could be due to just the lifetime of the lamp degrading over time, or an intensity drop due to lamp failure or any other kind of failure. And automatically the secondary device or the backup device would initiate, and you would not have a loss in measurement. So with this automatic lamp switching, you also have automatic lamp monitoring, temperature, and automatic shutter control of your device. And this can ultimately be interchanged very easily, the lamp exchange in this case here, and they have lifetimes up to 60,000 hours total lifetime. And depending on the application here, we tailor the light source to fit the needs of the particular application, whether it's 1.5, 5, or 7 watts. I also mentioned a ultraviolet visible solution in my previous slide for A to T ratios. This device that you see here is an example of one of our demonstrator UV-Vis instruments. And it utilizes some key features here. It utilizes robust detector array technology, which introduces essentially no moving parts to the process, where everything is fixed. And this allows for ideal stability for the measurement, and ultimately complete spectra can be acquired on the order of milliseconds without introducing any lag. These devices are also permanently wavelength calibrated. So once an instrument is installed in the location, it is permanently wavelength calibrated, and no shift in the wavelength is anticipated, and ultimately a set and forget device when it comes to the wavelength calibration. And the accuracy of this device is on the order of 0.2 to 0.3 nanometers when it comes to your wavelength accuracy, with a resolution of 3 to 10 nanometers. And these devices are fully process capable to any control system, whether it's a PLC or DCS. And these examples include OPC, Modbus, Profibus, 4 to 20 milliamp, etc. And then ultimately, these devices can be connected to your DCS or SCADA or PLC and introduce closed loop control so that you have automated feedback based on a result. So this is an additional feature of our devices that is pretty unique, and this is the embedded platform. So we refer to it as our TechSAS platform, and that SAS is spectrometer as a sensor. And this device here is independent of any host computer for operation and control. So ultimately, the spectrometer is connected to a PC just to parameterize the device and load any sort of modeling or calibration to it. And then ultimately it's disconnected from a PC and is left in a standalone mode for process control. So that is in large part due to the embedded operating system that is within the device, and the programmable calibration model, again, that you perform during the parameterization portion of the process. And then integrated within it is the ability for connection to process control interfaces such as Modbus, and ultimately allows for real-time data logging and analysis, as I've mentioned in the past. So here's just an example of the the structure and the layout of our Texas devices, which, all of our, as I mentioned, all of our equipment that I've discussed today is equipped with the Texas embedded electronic devices. So this is comprised of a spectrometer sensor, an MCU, an FPGA, and memory. And that is virtually the entire structure of the board, and interconnects via the interfacing options here, where ultimately, again, the result is just directly reported to a DCS or PLC. So I've talked a little bit about the solutions today for winemaking. I mentioned some of the disadvantages or the pitfalls of laboratory analytical methods such as HPLC, GC, and densitometry. And that includes the lag time, ongoing costs, and destruction to the sample, as well as some of the advantages for Tech 5 USA spectroscopy solutions, where you can quantify several components simultaneously. There's no sample preparation required, and it allows for immediate quantitative results and ultimately a very cost-efficient device. And today, again, I've discussed solutions for glucose, ethanol, anthocyanin, and tannin, and there are several additional parameters that can be monitored with this. And finally, looking to the future and current, additional applications that are underway include flavor profiling. So looking here, you can see, the aroma wheel and some of the corresponding chemicals that are responsible for some of the flavor profiles. So primarily in the fruit, floral, and herbal, there are the chemicals including esters, pyrazines, terpenes, and thiols, which all have fairly good near-IR absorbance, as well as in the spice flavor profile. This includes, again, some terpenes, lactones, and thiols. And then in the earth flavor profile, this primarily includes sulfur, acetic acid, and phenols. And all of this can contribute to the flavor profile of the end product. And some of these use cases for flavor profile are not limited to, but can include subjectivity removal. So ultimately, being able to have a conclusive idea of what the aroma or what the flavor profile of your wine is going to be. And you can do that without having to really taste the wine or having to perform these very intricate taste testings. And also an additional use case is for counterfeit detection. So many of you might know, replacing certain wines with sweeteners or something to mask the flavor profile and try and pass it off as something else. But with spectroscopy, identifying these key parameters within the flavor profile can ultimately help with counterfeit detection in that case. And that is coming to a close in terms of the presentation. If you guys always feel free to contact me. I have my email address below, as well as our number, and please feel free to contact us via the website or take a look at our website. And with that, I would love to open this up to any questions that you may have. Thank you.
Great. Thank you so much, Dr. Muraca. That was really, really informative. Appreciate those great insights. We do have some questions that have come through that folks, would love your thoughts on. The first one is around the margin of error on analysis. So can you talk a little bit about sort of what that margin of error is on the readings and sort of a little bit more about that?
Yeah, absolutely. So the margin of error is largely dependent on the concentration. So we can, with some of these technologies, we can achieve fairly low concentration levels on the ppm scale. And as you go to higher concentration levels, the margin of error only improves. But when it comes to the margin of error in this case, we've been comparable to that of the laboratory analysis. So, those margins of error that you would get in GC or similar to that, we can be on the order of comparable to those margins of error.
That's great. We've got a couple of questions around keeping things clean. So how do you keep the sampling windows, the probe, measuring device, how do you keep everything clean so that readings are consistent over time in a messy commercial setting?
Yeah, keeping things clean, that is a great question. There are a few ways that our end users keep things clean and that we introduce solutions to keep things clean. One method is by, I mentioned earlier, introducing this slipstream into the device. So what a lot of people tend to do is by introducing the slipstream, you can ultimately valve off the measurement and introduce a cleaning solution to the probe and a cleaning solution to your measurement location. And a lot of folks who have clean in place do this quite frequently, and it's a good way. And as a second method, we have the option of retractable probes. So we have retractable devices which ultimately can pull the probe from the process and administer the cleaning solution independent from the process. And then when this has been completed, this can be reinserted into the process, and you have a clean device in this sense.
That's great. Quick follow-up to the first question around sort of margin of error and comparison with regular wet chemistry. Do you have a data comparison that's available that shows that?
We can have a data comparison, and that's something that I can share with you, with anybody who's interested offline. But just to speak on it very, very roughly, these results can be comparable where you have certain targets that you need to achieve, and if you're within this percentage or so, this is ultimately enough for the end user. So, laboratory measurements can be, are a little bit more detailed and a little bit more intricate, but ultimately spectroscopic methods get you where you need to be.
Great. Let's see, we've had another question that came in around data analysis tools. So the question is, the assumption is that do users need to have their own data analysis tool, or have you partnered with any other current service providers who offer spectral analysis or the like?
Yeah, a great question again. Tech5 USA does have its own operating software, but when it comes to the partners, we have a few different partners when it comes to chemometric modeling that we directly can interface to. So if those of you who are familiar with some of the partners out there, we've interfaced our software directly with their software in order to be able to work seamlessly and have this direct connection so that you can optimize your results. So ultimately, if there are additional partners out there, we have set up projects that those can introduce it, but we've already partnered with quite a few of the major ones out there.
That's great. Turning it a little bit back to sort of the fermentation process, got a couple questions around that. First, around whether your tools work with grain fermentation. Can they be used sort of for that means?
So if I'm understanding grain fermentation in the sense of these solid particles and these solids being in it, or I guess maybe it is, I'll answer it in the two ways. So the first way, if the assumption that they are solid grains that are present, and then the second one, for different applications, in the grains. So to answer the first question, these particulates and these solids are typically can be filtered out during this process. And a lot of these solids actually do settle into the bottom of the tank in this case. So for those particular applications, we've installed probes to the top portion of the tanks and the vats where these settlements are not taking place. And as a secondary, we've also introduced filtration systems to a lot of processes that require it. So that's one thing. And then to address the secondary portion of the question is we have had a lot of different fermentation applications where, of course, ethanol is likely a major product. So we're not just limited to the wine industry. We can introduce our devices to a lot of different applications, especially in the fermentation space.
I think that will be very exciting to folks in our membership who engage in other forms of fermentation. So that's really exciting. Question around that came in around making wines from wild yeast. Is it possible to stall or capture the flavor when it hits an optimal point? I guess the question is it possible to stop the yeast without affecting other parameters?
Yeah, that's another great question. I think I touched on it a little bit very briefly about the flavor profiles that are possible. Yeah, you can ultimately have these various flavor profiles as a result, and it's not required to stop the yeast process. This can be a background parameter in the analysis and the modeling, as long as it's understood that the yeast is playing a role, and what role it's playing, it certainly does not influence the flavor profiling in terms of measurement.
That's great. It looks like we had another question come in. Sorry, we had a couple come in that pushed these down. So give me one second here. Great. Actually, I think we've touched on all of these in one way or another. I've got a question for you since I'm not a winemaker and I'm very curious sort of how robust the technology is. Are we at the point where measurement alone can sort of guarantee the flavor profile of the wine? In other words, you sort of mentioned like, hey, maybe without even tasting it, you could know sort of what its flavor profile is going to be. Are we at that point, and is the tool sensitive enough that that's possible?
Right. So again, a great question. I also am not a winemaker. I'm a spectroscopist applying to wine, so I would never step on the toes of those who are true winemakers out there. But ultimately, this can give a great indication of when a flavor profile is reached, or when an ethanol level is reached. And ultimately, if not completely replacing those taste testing and those critical tests, at least reducing them. So, there may be a need for an end user to want to check the quality every so often, maybe send out it every few batches instead of every batch or so. But we don't want to completely replace it for those tried and true winemakers who still want to test their batch, but at least we can reduce the amount of samples that need to be sent out for testing, and that's the goal.
Excellent. One last question here around working with food regulators. Have you seen these analysis and these tools used when working with food regulators at all to sort of help make the case one way or another in terms of ethanol content or otherwise? Yeah. So what are your thoughts on that?
Yeah. So I know it's a very regulated industry. And we do seek to comply to any of the norms that are set by the industry. We have implemented, stainless steel devices, so they comply with any hygienic norms that are required by the industry. And we've also, we've introduced quite a number of hygienic probe designs that can be introduced as well. So really it's a matter of meeting the needs of the industry and really just staying in touch with those, those regulators and those who are responsible for introducing these things.
Excellent. Well, with that, I want to thank you so much, Dr. Muraca, for sharing your knowledge and experience with us. And I want to thank everyone for attending today's webinar. And thanks again to Tech5 USA for sponsoring this session. We will post a recording of it on our website in the next 24 hours. We'll also include contact information for Dr. Muraca should you want more information about Tech5 USA and their offerings. Thank you so much for your engagement with the Fermentation Association. Look out for our biweekly newsletter. Check our website, check out our YouTube channel, subscribe to our YouTube channel, and stay connected with us on social media. Enjoy the upcoming holidays, and we hope to see many of our new members, many of our members in the new year as we continue our webinar series. Thank you so much, everyone, for joining us.
And thank you very much, Mo. Bye-bye.
Goodbye.